Hello everyone and welcome to the video on escapements for Gurotic Thoughts. This new escapements module has changed some from the escapements of Gurotic Motion. This one is a bit more exact and it's written to a higher specification. Calculations for both the recoil and the gram are taken from the British Horological Society calculation test sheets. So the mathematics involved are very accurate to those specifications. The drawings of the pallets are somewhat stylized from acceptable versions. I did not aim for a crown and anchor, for example, on the recoil, but there's specific reasons why I've gone this route, and we'll talk about those in the future. 4 types of recoils are being offered. Grasshoppers are not yet in the mix. They will be added at a future time, but grasshoppers are complex enough I'd like them to have their own module so that we can play a bit of games with giving you some more power with them and add those to gravitic escapements. We'll give you more escapements in Gurotic Thoughts than you ever had in Gurotic Motion, as there seems to be a great deal of interest in it. So let's look at the 4 that we have offered. You can see the one running on the screen now is called a recoil escapement. It is the easiest escapement to build. These 4 escapements are listed in order of complexity to build, and recoil would be firmly in the beginner camp. Anybody can build a recoil escapement. If you have a pair of scissors, you could cut this from cardboard and it would run well. They are notoriously stable. They are not, however, the most accurate timekeepers. The reason for this is if you look at this ratchet, the center device here is really called a ratchet. And if you look what happens when a tooth comes down, you'll see the ratchet goes backwards for a moment. This is called a recoil. This recoil creates a situation where you lose accuracy in clocks. It's because when the pendulum goes to push the recoil backwards, the recoil is pushing against the backlash of all the gears before this one. And since backlash grows and accumulates over time in a clock or a timekeeping piece, it means that the accuracy of the pendulum degrades over time as well. It slowly begins to degrade, and every few months you have to retune a recoil clock for accuracy. Now, that having been said, many of the things you'll build with Gurotic Thoughts, including wooden clocks and so on, the point is not about their accuracy. There is no such thing as an accurate wooden clock. They all are bad at keeping time. They vary in how bad exactly, but they're all bad at keeping time. But when you build a wooden clock, the point is not to tell time. Wooden clocks are a piece of craftsmanship. They're an art form, a kinetic art form. I'm starting to go the other route and building clocks that don't tell time. I call them tickers. You'll find many examples of them on the web, and I find them intricate works of art. And again, they don't tell time, so you wouldn't have to worry about inaccuracies in time. However, take it from me, the people who build clocks will tell you that though these recoil clocks are easy to build, they are not the best timekeepers because of this recoil action pushing against backlash in gear trains. Now, we have several selections on the screen. You'll see it's not tied to module anymore. People who are building clocks will generally build this escapement mechanism to a set diameter. They're not really worried about the module of teeth and so on. So Gurotic Thoughts has gone to a diameter system where you enter the diameter of the device that you wish to build. Here, for example, we have 4 inches and it's set to a 4-inch diameter. Now, number of teeth on your ratchet, on this recoil ratchet, are set down here on the tooth box, and you'll notice as you change the number of teeth, the listing for pendulum swing changes. The amount a pendulum will swing on a recoil escapement is typically set by the mathematics. So we're simply telling you that you're going to get a plus or minus 2.08 degrees of swing when this pendulum has hit its equilibrium and is keeping time. For the recoil escapement, you can ignore the next 2, back angle and forward angle. Those are used only in a forward ratchet, but we'll talk about those in a moment. Let's take a look at this in close-up. The ratchets can be hard to build in 2.5D out of wood and other materials because too pointy of a tip will snap off easily. If you picture that this ratchet is made from one plank of wood, for example, and not plywood, the grain of the wood would always be running in one direction. If you get a tip of a tooth and it's on a grain which is running in the right direction, you're going to snap the tooth off, unless you've got a fairly good tip allowance to it. So because of that, we have a tip relief where we can set the number of degrees of tip relief. And you can see as I change it, the size of the tooth of the pallets on the recoil pallet change. And this is because we have to worry about a thing called drop and lock in such escapements. So I'm going to turn the tip down to about 1.5 degrees, which is pretty typical when I'm cutting something out of wood. So I guess what we should say is the more tip relief you have, the less power you're going to be transmitting to your pendulum, because as the tip gets larger and a higher degree, the pallet size has to get smaller to be able to fit in between the teeth. So obviously, the more room you have between teeth, the larger the pallet impulse face can be, and the more power you're going to transmit to a pendulum. Again, if you're making a piece of kinetic art, this may not be too important. Your overriding concern will be to get a thick enough tooth to provide stability to whatever you're building. And the amount of power you're transferring will probably be a bit secondary to your consideration. If you're building a clock, however, you want as much energy transfer to the pendulum as you can get to maximize the length of time that your clock will run on a wind in the end. I can tell you 1.5 degrees is, again, pretty typical. So watch what happens as we simulate this. We have our 1.5 degree tip relief, so the lengths of our pallets are changed, but watch this tooth as it comes down, and we can see it just misses. If we change the drop angle to 0, you can see that the tooth here on the right is just touching the ratchet tooth, and this would not be very good. You know, at some point, looseness and tolerances in these bearings and so on, the tooth is going to hit. So because of that, we'll add a little bit of drop in order to make sure that the tooth will miss, and I'm going to go with about 0.5 degree of drop, which is typical. Tip is actually included in drop. So we have 1.5 degrees of tip and then 0.5 degree of drop for a total of 2 degrees of drop. That's getting about the upper limits of what you would want for the sake of efficiency in transferring energy to your pendulum. But just make sure with your drop that you're missing this tooth as the recoil comes down. We hit, it recoils, tooth slides off, and process repeats itself where we just missed the tooth. That's drop. So that's all we really need to worry about in terms of a recoil. We have a lock adjustment to worry about, and the number of teeth and the span that you wish to span. These are all decisions up to you based on aesthetics and however you want to time your device. Typically, a recoil escapement has around 30 teeth and has a tooth span of about 7.5 teeth of a 30-tooth wheel. How you pick the number of teeth of this depends largely on the ratios you intend to use in your clock, and we'll leave that for a future video. But that's a recoil escapement in general. You'll notice there are many other settings down here. They'll have no effect on a recoil. A recoil is so simple that all there is teeth, tooth span, and lock. That's really all you need to worry about. So then it's off to the Graham escapement. The Graham escapement was a way of fixing the problems that a recoil escapement had in its losing accuracy because of the backlash of the train. You'll notice that the ratchet here does not move backwards. It moves only forwards. This is why it's called a deadbeat escapement. It is dead when the clock beats. The ratchet wheel never goes backwards. But we have things to worry about because of it. The reason that we have a ratchet which doesn't go backwards is because of these rounded lock faces on the pallets. You'll notice that because they're rounded, the tooth comes up and hits, and it's at a tangent relationship. It never has to go backwards as this moves back and forth. Let us take a look at one tooth and see what we have to adjust here. You'll notice as this tooth comes down, it hits this face, and there's a large portion where it sits still before pushing on the pallet. This wants to be minimized, but you do need some, and this is called the lock adjustment. The amount of lock you have is basically how many degrees of the lock face of this pallet which you are striking on when the tooth comes in. And down here on lock angle, you'll find I'm set at 2.5 degrees, which is quite a large portion on here, and that would be an unusually large. If I cut it down to 0 degrees, you can see that what happens is when the other side releases its tooth, this tooth will come up and hit the pallet exactly at this corner. This is a situation you wish to avoid, because again, if there's any inaccuracies, remember that at this moment in time, this pallet is swinging downwards, and you don't want to crush this tooth if the tooth just happens to get underneath it. This is why we add lock. So let's add a little bit of lock. 1 degree, 1.5 degrees is pretty typical, and right there is good. This means that when this tooth snaps forward, it's going to hit this lock face with lots of room to spare. We're not at risk of it going underneath the tooth and getting caught or jammed. That's the best situation to have. We have a similar situation on the other side where we do have to worry about the drop as well. And you can see I'm set to 0.5 degree of drop right now. 0.5 degree is not bad because we're adding it to the tip. So we have a total drop right now of 1.5 plus 0.5 or 2 degrees of drop, which is a pretty good place to be. Those are the only adjustments that you really need to worry about on a gram. A gram is much more accurate. It doesn't have to push backwards, and it will keep time without adjustment. Once you adjust it for accuracy, it's unlikely that it's going to go out of accuracy for the reasons of backlash. So it is considered a better escapement than a recoil, a more accurate escapement than a recoil. But again, if you're going to make something out of wood, you're not building it for accuracy, so you'll have to make a decision whether a gram is actually better for you than a recoil, given that a recoil is much easier to tune in and make run for good. As you can see by looking at this gram, your accuracy requirements are a bit higher, and that's why the gram is the second escapement, or a more advanced user's escapement. These teeth have to fit exactly in their spot. You must do a good job of shafting and bearing to make sure that everything is structurally sound, because any motion in the distance between these shafts may cause a situation much more easily than a recoil where you stop ticking. So again, recoil, no problem. It would be hard to mess this up. On a gram, you have to give a bit more thought about what you're doing, and that's why I advise that if you're going to build a gram, build it after building a recoil. The recoil will teach you a great deal about how to make things strong enough to run as a clock, where the gram, once you've learned those lessons, you'll find that the gram is very easy to build, and it is much more accurate. It's up to you whether or not you're going to try for accuracy or try for other factors, other aesthetics in what you're building. And these two escapements really give you the choice between accuracy and ease of use or stability over time. These are the two best escapements to use for building a timekeeping piece. And that leaves us with chronometer escapements. Chronometer escapements come in two flavors. One is a deadbeat chronometer, and if we simulate it, you'll see that the ratchet never moves backwards. So just like in the first two examples, this one would be closest to the walker. It has a lock face, as you can see, this round edge. Although this lock face is actually never used. It is actually just a safety face to keep this wheel from running down should it become accidentally unlocked. If we stop the simulation and zoom in on it, you'll see the teeth actually never touch that safety face. They would only touch it if this lock face were to snap off or snap away at the wrong time. Then these teeth would come in and hit the wheel and stop the device without causing damage from a wheel running too fast. So in a chrono, typically there would be a spring on this wheel, which will cause the wheel to rock back and forth. And as it swings in one direction, it flicks a spring out of the way, the gold spring it's called, and in the other direction it will hit the spring, cannot flick it out of the way because it's in front of an arm. It will flick the arm to the side, thus releasing a tooth, causing the wheel to turn. And it's synchronized with this impulse pallet with a hole cut out of it so that the tooth presses here on the pallet, adding energy to the spinning pendulum. So if you think of it in classical terms, it is simply adding energy to the pendulum, which then swings back. It's ignored in one direction, and then energy is added again in the other direction. That's one use of a deadbeat chronometer. If you were to take away a spring, though, and put a wheel on it so that the wheel was free to spin, what would happen is it would get to this point, it has energy, it would spin all the way over, at which point it would trigger the wheel again and spin even faster. And what you would have is a kinetic engine, a unidirectional kinetic engine that slowly ticks down the teeth of your spring while keeping a wheel spinning. And depending on the speed you have this wheel spinning or how it's geared down to whatever output mechanism you're using, this means that you could have a wind-up device which runs a motor for a very long time in a single direction. The last type we're going to look at, and the type I decided to use in my toys, is the recoil chrono. And if we look at it in simulation, you'll see it's basically the exact reverse of what we just saw. In this one, when the pin comes around, it's going to strike the tooth out of the way, which causes the ratchet to hit the face and stop its motion, reverse it, and send it back in the other direction. At which time it will repeat itself. Now again here, I've got it simulated as if it were on a spring, but that doesn't have to be so. Imagine that the tooth presses on the wheel and there's nothing to stop it. This wheel would then continue to rotate counterclockwise several times until it runs out of steam. When it runs out of steam, the heavy part of the wheel will always end near the top of travel and then come back down, and on as it swings back down, it will hit the tooth, release energy, and repeat the cycle. And that is the energy cycle of something like Gearotic Ticker number 1, which you've seen at the beginning of this video. But we have it drawn here as if there is a spring on this wheel and it's rotating back and forth. Now the best way to explain these, however, is in 3 dimensions, because this is a 3-dimensional device and it's very hard to look at in 2D. So let's create one and add it to the screen so that we can see exactly how it works. As you can see, the trigger arm actually sits away from the ratchet. It's over here, and it holds a tooth. How you bolt it on depends on, of course, what you're making, and that's another point. These are complex enough devices that although Gearotic Thoughts is very handy in that it'll give you the centering locations, an exact template, and it will cut out the ratchets, when it comes to these pallets, it's giving you perfect numbers. That is to say, it's making this wheel the perfect diameter. And you're going to find in practice, like when, for example, when I built my Gearotic Ticker number 1, this would have to be shaved down by probably 1 to 2 millimeters in order to allow for sag tolerances of shafts and so on. So keep in mind that all of these things are to perfect specification, and you're going to want to modify them some as you build them, but they're essentially very simple devices. They are circles with a pin in them or with a notch cut out. So these are things that you will fabricate for your devices as you go. Same thing for this trigger tooth, which is holding the ratchet in place. How you come up with a trigger lock is up to you. On a construction device like the one I made, you need to have it adjustable back and forth in this dimension in order to fine-tune where these teeth will sit against this wheel when the device is moving, because again, as you can see when we zoom in, these teeth are not meant to touch this wheel. This is a safety wheel. So you're going to want something which can adjust this tooth up and down slightly in order to maintain this balance. Here you can see our spring, our gold spring. So in simulation, as the pendulum rolls back and forth, the pin is either going to push the arm out of the way, which will then cause the ratchet to add energy to this pendulum, or it will flick this spring, having no effect whatsoever on the ratchet or the pendulum as the pendulum uses up its energy. In order to show this a bit better, we can add a spurred gear to it. I'm going to go to Tools and get a large enough spur gear that we can just add that to our project, and we'll add it to where it would be. You can also, on any spur gear, right-click it in the project window and say Strip Teeth. And once you strip the teeth, it begins to look more like a part of a clock. But that strip tooth gear, I know some people have wanted it for a while anyway for other projects. That is available as of the last version. So now you can see this is what a watch typically looks like when you open it up. You would also see a coiled spring here, causing this wheel to turn one way and then the other. In Garrotic ticker number 1, we don't put any spring, so what happens is the wheel, once it gets kicked, will rotate counterclockwise many times, flicking the spring each time, having very little effect on the wheel. But eventually the heavy part of the wheel will end up near the top. It can't quite make it over, so it falls back, and when it falls back, it releases the arm, which triggers another cycle. And that's the essentially the way a lot of kinetic art works. Kinetic art that uses escapements, this is a pretty classic escapement. There are 2 or 3 others that are common, and I do hope to give you examples of those in future as well. But in future, we'll give you the escapements as I get myself.
All that having been said, I think we have to look at one final thing when it comes to chronometer escapements. We have to look at the actual construction details, because unlike many of the things that GT puts out, we're getting into an area, and I think it'll happen increasingly, where we're putting out things too complex to show you every bit and part. So a certain amount of construction expertise has to be developed. For example, take a look at the trigger arm on this drawing. We hadn't really talked about the trigger arm, the fact that the trigger arm has to spring back to 0, and you'll notice a very small post, this small brass rod sticking out. This is what the trigger arm, when it swings back in towards the ratchet, is going to bottom out on, so that it doesn't come in too far. And this is a post that I just have shoved into the background skeleton frame. So you have to take note that things like a trigger arm are going to have return springs and so on. I will be making a separate video on the building of this particular ticker, and we'll go into a lot of the construction details then. In the meantime, take a look at this video.